Hello, and welcome again to another video about Unit 3 probability calculations. In this video, we will study the Morgan laws, which may be very useful for the resolution of some specific problems. These laws are based on the decomposition of some terms that are negated. That means that we are working with the complementary expression of the union or the intersection of events. These laws were proposed by Augustus de Morgan, and as you may see here, these laws are based on the decomposition of two events that are related somehow, could be through a union in the first law or through the intersection in the second law. And the main idea of these laws is that we can decompose each of the events included in the negation in the formulation of the complementary event through the decomposition into the intersection of negated events, as this is first law, or the union of negated events. When we refer to negated events, we are talking about complementary events, no A, no B, that includes all events that are not included in E. This is something we reviewed, we defined in the first videos of this unit. If you don't remember this idea, please go to these units and review what does it mean, the complementary of A or the negation of A. I would like to show you some definition which is quite intuitive about how this first law and second law works. Imagine that we are considering the area that's defined by the union of A and B. So, if we consider the union of A and B, you know that this is the area, this is the shape given by the addition, the union between A and B, as it is shown here. So, if we want to obtain no A or B, what we need to do is to consider the area that remains between no A or the area that remains between no B, which is no B. Here in blue, we are excluding no A and no B. Here with the letters in red, you may see which would be the area corresponding to no A and the area corresponding to no B. Thus, if we want to obtain the complementary of no A or no B, then what we should consider is the area defined by the intersection, defined by single events. So, as you may see here, the area provided by no A or no B should be the area given by no A and no B, and that's the definition, that's an intuitive definition of the first law. So, for the second law, it's the same idea, but now we are decomposing the intersection between A and B, negated, which is going to be given by no A or no B. So, if we want to define these ideas, we should consider, first of all, the area given by the intersection of A and B. All of you know which is this area in blue, that's underlined there. This is the intersection, the joint probability of A and B. And to obtain this probability, we should consider the area provided by no A and the area provided by no B, which is this remaining area in blue, which were marked here in these two schemas at the bottom of the slide. So, if we consider the union of these two areas, then we would obtain the union of no A or no B. So, here we see how it works, that the intersection, the complementary definition of the joint A and B can be obtained as no A or no B. This definition aims to be some help for you to understand how the laws work, but for the resolution of problems, you can use the formulas that will be available in the formula sheet and use them for solving problems, as we are going to see. Imagine this example. We have been considering some use of clocks for attending to work. We are working with the timetable of a recently graduated engineer, and then he needs to go to an interview. So he has 5 different alarm clocks, which are called A, B, C, and E, and we have the probability of failure for each of them. That is given in the description of the problem, such as for E is 0.5%, for B is 1%, for C is 0.5%, 0.5, 0.5. All of them are the same, except for clock B, which is a bit higher, it's 1%. So we assume that the graduate will fall asleep, so he won't get up spontaneously if no alarm rings. So to avoid this, he decides to activate more than one alarm clock. So the question is, if we have 2 clocks to be activated, clock A and clock B, what's the probability of falling asleep? We would define P of A and P of B, as you know, as we studied some videos before. We will say even A is the alarm clock, it's operative, so it works well. And we know that the probability of A, that the clock works, is 0.09095. Why? Because this is 1 minus 0.005, which was the data given in the problem. And for B should be something similar. The alarm clock is operative, alarm clock B is operative, and the probability that it works well is going to be 0.99. Okay? So the probability of falling asleep should be the probability that A fails, clock A fails, and also clock B also fails. Both events are defined simultaneously. So falling asleep is defined as the probability that A or B, they do not work, and this is defined as the probability of no A and no B. We are assuming that the clocks are independent, and this is something that it's deduced, it's obtained from the definition of the problem. So this can be decomposed as the probability of no A per probability of no B, applying the probability to be independent. So if we substitute the probabilities for each of the events, we will obtain this small probability, which is the probability of falling asleep. That means any of the clocks are working, A and B, and that means that eventually he will arrive late, which fortunately it's a very small probability. So with this, I finish this presentation about the Morgan laws. Thank you for your attention.